Great. Good morning, everyone. I am Jimmy. I'm Professor Jimmy Adegoke. It's morning here in Kansas City, but you might be joining us from somewhere else where it's afternoon or maybe even evening. So good morning, good afternoon, good evening. This session is on coastal erosion. It's a parallel session. There are 3 other sessions going on right now, but you're welcome to this session. We have a distinguished group of panelists that are going to, global experts on the issue of coastal erosion. And they're going to take us through their experiences and their outcomes and research from their research and work from across the world. So without much ado, I'm going to go right into it and introduce our panelists. We have five panelists in this session today. We have Goncalo Vieira from University of Lisbon in Portugal. We've got Landim Dominguez from Brazil. We've got Sérgio Ávila from the Azores, University of the Azores in Portugal. We have Christine Omuombo from University of Kenya. And then Joni Backstrom from University of North Carolina in Wilmington, United States. Okay. So I want to just also mention that, so this session will run for about 30 minutes, an hour and 30 minutes. Each panelist will have a presentation for about 10 minutes. And then after that, we will have a question and answer session. So as the panelists, we'll go through all 5 presentations. So that'll take us 50 minutes. If you have questions, please use the chat box, the chat feature of Zoom, and we will keep track of those questions. And then we'll select a few of them so that the panelists can respond to those in about 15 minutes on the backside of the presentations. And then, importantly, the official program session, they will end in an hour, 30 minutes, but we would move on into a breakout room and continue this conversation so that we can respond to the additional questions, and that will last for 30 minutes. So actually, this thing is set up for a 2-hour span. So please, you don't have to do anything, just stay where you are. After the end of this program, this portion of the program, you will be automatically moved on to the breakout room, and then we'll continue the program there. My pleasure, ladies and gentlemen, to invite our first panelist, Goncalo, to please give his presentation.
Good morning, good afternoon. Jimmy, I hope are you listening me well?
Yes, I can hear you very well, okay. And I believe our audience is also hearing you well.
Okay, perfect. So I will be sharing my screen. Can you confirm that you are viewing the screen?
Yes, sir.
Okay, so it's a big pleasure for me to be involved in this panel today on coastal erosion. Me myself, I'm a permafrost scientist. I work mainly on frozen soil in Antarctica and in the Arctic. And since about 3 or 4 years ago, I started also working on coastal erosion issues associated to permafrost in the Arctic. So my talk will be focusing not directly in the Atlantic Ocean, but in the Arctic Ocean. It will be essentially targeting remote sensing, both in situ observations conducted by drones and also satellite platforms, different kinds of platforms, and some applications that we are conducting in the framework of an European funded project, the project Nunatariuk, and also another project funded by Canada, the Climate Change Preparedness in the North program. These activities that we are doing, they deal with coastal erosion, but also their impacts on local communities, and the way we are targeting the research there in the Arctic can also be applied successfully. And of course, it is being applied by other teams successfully in the Atlantic Ocean area. But we aim also to bring up some ideas for discussion and also to do some knowledge transfer into this Air Center initiative and to the All Atlantic Forum. So I will be speaking about essentially what we are doing there in the Arctic, giving you a brief introduction to the problems in the Arctic. And the focus will be on what is happening in the Arctic coastal zone. Essentially, we are dealing in the area where I'm going to give you some examples with bluffs, which are essentially carved on glacial deposits, moraines, but also some non-consolidated sediments. But since this material is frozen, it behaves really until it stays in the frozen state. It behaves as if it was a rock. So we really have vertical bluffs, but then it's also very easily affected by issues associated with thermal erosion by the water and by slumping and degradation of the permafrost. So it's really a very active area and very interesting. And this project, the project Adegoke, it really assesses permafrost thaw in the Arctic and the changing Arctic coast. And we have a focus on science and also on socioeconomic adaptations. And this is where I think there can also be some interesting notes from what we are doing with local communities into the Atlantic Ocean realm. Of course, it's a very large team. We are more than 20 institutions, but in the coastal component, we are working mainly with the Alfred Wegener Institute and also with the Geological Survey of Canada. Some of my colleagues the main collaborators are indicated in this slide. And the project is aiming to better understand what is going on in the coastal area, all the interactions between the ocean, the coast, the rivers, nutrient fluxes, carbon fluxes, and its impacts on the climate system, but also on contaminants and on the people who is living there. So this image, I brought it here just to frame the Arctic Ocean and its linkages with the Atlantic Ocean, mainly with the North Atlantic. We will be working, I will be showing you results from this area near the border between the US and Alaska and Western Canada. In the Yukon coast, most of the examples will be shown from the Yukon coast, but also from the Northwest Territories. And we can see that there is a linkage between the Arctic Ocean, mainly through the Frame Strait, interlinking with the North Atlantic, and also important exchange fluxes of water flowing northwards into the Barents Sea and also through the Frame Strait and influencing what is going on in the Arctic. The Arctic is changing fast. Climate change is really affecting much stronger the Arctic than elsewhere on Earth, with the process which is called Arctic amplification. And essentially what is happening in the Arctic in what concerns to warming, it normally doubles the rate of the average warming elsewhere on Earth. If we look at the Arctic sea ice extent, I'm not going into detail about this, but just to remind you that there has been going a continuous decrease in Arctic sea ice extent every summer, and in this summer we have just recorded the second year with less sea ice extent in the Arctic, with several predictions in different scenarios showing that we will probably be facing an Arctic free of ice during the summer. So this sea ice free environment in the Arctic Ocean will lead, and is already leading to essentially a longer storm season. There is a much longer season where the ocean waters are suffering the influences of the weather systems. So the longer sea ice freezing implies also a larger fetch, increased storms, and also what we are experiencing also are warmer seas. So the water is also warming up, with strong implications in the coastal area. And of course, some of the areas of the Arctic, not all, are experiencing also sea level rise, but this is of course depending on its location and essentially associated to the glacio-isostatic rebound balance. So the Arctic is changing fast and is closely interconnected to the Atlantic. Moving into permafrost. Permafrost is essentially perennially frozen ground which stays frozen for centuries or even millennia or even more. completely frozen. And in the Arctic, surrounding the Arctic, we have coasts of frozen ground, of permafrost, which encircle the Arctic Ocean. This map gives you a glimpse of a survey done in 2012 on the dynamics of the coasts in the Arctic, and we can see that there are significant stretches of the Arctic coast, like for instance the area we are studying, which are suffering increased erosion, which can really be quite quick, with up to 2 to 10 meters per year, or in some areas even more. There are areas which are experiencing more than 10 meters of coastal erosion in bluffs per year. One of the main issues of the implications of these is that these permafrost coasts are many times or frequently rich in carbon content, and what is going to be the fate of this carbon, it's still an unknown, and we are trying to better understand what is going to happen to these coasts and how the carbon is going to move from the land, which is isolated from the climate system, into the ocean and into the climate. So we have an image here of a typical coastal section. We can see that the sea is right here, and everything is falling apart. You see the bluff melting. There are small slumps in some areas. The slumps are really large, more than 1 kilometer wide. And this image, which is moving on the lower part of the screen, shows a few days of melting, of thawing of the permafrost, and the erosion going at steady pace, even without storms going on the ocean. So with increased storms, the coastal erosion rates are really increasing. Another image from the helicopter, where you can see a very active degradation. You can see the grass here from the tundra, and it's falling, and it's really moving quite fast, and strong degradation. We are focusing on several initiatives. One of them is related to collaboration with local communities, essentially indigenous peoples, hamlets, Inuit communities, in fact, Inuvialuit communities here in the north, some of them pretty remote, with no access by road. For instance, Polotak, you have to fly 300 kilometers by aircraft to get there. So there are issues related to coastal localities, which are also possible to be found elsewhere in remote coastal regions on Earth. And we are doing collaborations with these communities and essentially assessing how the coastline is changing, how fast it is changing, collaborating with the Geological Survey of Canada in order to provide baseline data, both from high-resolution drone surveys and also high-resolution remote sensing surveys. So there is a very close interaction with co-design and co-production of the project on these hamlets, and I'm going to show you some examples of the quality of the surveys that we did. So with UAVs, we are able to have very high resolution, in fact, ultra high resolution surveys almost immediately. This survey, which I'm showing you, is an effort that allowed the production of this very high resolution orthomosaic with base resolution of 2 centimeters, but then it was resampled to 10 centimeters. This orthomosaic and also the digital surface model, which you see here, has been provided to the community, and it's being used currently also to produce flood mapping, because there are storm surge events with flooding in the community, and we are working with students from the University of Lisbon, also co-supervised by Geological Survey of Canada, and with collaboration with the hamlet of Taktayaktuk, where we go with the local communities to the field. We discuss the areas where the flood levels have attained at a certain date, and then we integrate these in a GIS. We use also tide gauge data and our very high resolution surveys with the drones, and we really obtain accurate survey, accurate modeling of the flooding associated with storm surge. Furthermore, we also want to improve the volumetric estimates on coastal erosion, because we want to know how much carbon is moving from the coast, from the continent to the ocean, and then its fate. And it's really important to know more than only the retreat rates, but also to estimate what goes out in what concerns to volume. So we sample carbon, we sample also contaminants from the bluffs, from different areas, and then we have several test sites which have been surveyed for several years by the Geological Survey of Canada. And currently we are applying different techniques there and improving these surveys. You can see the very accurate models that we developed. This is an example of an ill-shaded map, and you can really see the helicopter and its topography of the helicopter.
You have 2 minutes, sir.
Okay, I will go even faster. Thank you. So you can see here a comparison of some results with the drone and with coastal retreat of 80 to 100 meters in 8 years. 8 years time. Then we are also having some specific projects with new satellites that are being deployed, especially the PAS satellite, a Spanish satellite, which is microwave satellite. And we are using these microwave satellites at a sub-meter scale in these specific areas to monitor coastal change. The big advantages of microwave, as several of you will know, is that it allows you to monitor changes even in cloudy skies, which is really an advantage. And we are looking into intra-seasonal variability of coastal erosion with images taken at 11-day intervals. And finally, we have another project on coastal erosion at the regional scale, and we are working with the Pleiades satellite with 50-centimeter resolution with specific acquisitions. And this allows us to, at the regional scale, to see how coast is changing in the long term. And you can see here, this is the Mackenzie River Delta, and you can see really very high erosion rates of over 20 meters per year. And the final remarks, just wrapping up with this presentation, I wanted to show you how can high resolution remote sensing be transferred and be applied from remote areas in the Arctic, and this kind of knowledge be applied also in other areas in the Atlantic Ocean coasts. The synergistic use of field-based observations with drones and also satellite observations. We are also addressing issues from scratch in collaboration with these communities, local communities, which help us to build up the projects. So co-designing in these collaborative approaches. And in fact, this is with the COVID-19, we were unable to go to the field this season because of travel restrictions. And some of the local community people are working in this project, taking measures in the field. And I would like to emphasize that these kind of projects can be also very important for capacity building in order to teach local communities how to work with several of these features, essentially in what concerns to local validation and data collection. It can promote employment, and it can also allow us to do our research in our research institutes while also limiting our carbon footprint. Okay, thank you very much for your attention.
Excellent. We'll segue right into our next presenter, Landim from Brazil.
Okay, let me just, yeah, good.
I think you have to stop sharing your screen, Goncalo.
I already stopped. I think it was automatic.
Okay.
You got 10 minutes, sir.
Okay. So, good afternoon, everybody. I'll change a little bit from the topic presented by Goncalo, and I'll talk about coastal erosion across different spatial and temporal scales. The position of the shoreline is controlled by how the sedimentary record accumulates, and the sedimentary record by its turn is a result of combination of creation of accommodation space and sediment supply. Sediment supply is dependent on relief and size of drainage basins and on rainfall. If you look at this image, you can see that from Brazil, the region where you have the smallest drainage basins are just the northeastern corner of Brazil. And these basins, this drainage basin, besides being smaller, the relief of this area is also very reduced. So you can expect a low contribution of sediments coming from the continent. If you look now for the rainfall, you can see that also northeastern coastal Brazil is situated in an arid to semi-arid area. And the combination of the size of the drainage basin and the rainfall determines the sediment flux that we see here to the right. And you can see that the northern Brazil has a high sediment flux because of the Amazon and also all the large rivers. Eastern Brazil also has a high sediment flux because all wave-dominated deltas are located in this area, but the northeastern Brazil has almost no sediment reaching the coastline. The other aspect determining the sedimentary records is the accommodation space. And accommodation space was created during the last rise in sea level since the last glacial maximum. During the last 16,000 years, sea level rose about 120 meters, and that creates the accommodation space. So as a result, if you look in northern Brazil, which is a tide-dominated region, we have extensive progradation, as you can see here, mangrove progradation, tidal flats, in some places about 30 kilometers wide, because we have this combination of generation of accommodation space and a high sediment flux. If you look at the eastern Brazil, we also have extensive progradation of the shoreline, especially associated with the wave-dominated deltas, because also have a high sediment flux, and the accommodation space created was the same as in northern Brazil. So it's very common to find those large beach-ridge plains along this section of the coast. But if you look at northeastern Brazil, where sediment flux is very reduced, there is no accumulation of sediment, no accumulation of a sedimentary rock, although accommodation space was generated because of this eostatic rise in sea level since the last glacial maximum. So the coastline is characterized by sea cliffs and beach rocks, which are cemented beach sediments that were exhumed by coastline erosion. So the severest cases of shoreline erosion in Brazil are located exactly at this northeastern corner of the country. Superimposed on this large-scale control, the other two major causes of shoreline erosion or variability of the shoreline is the dynamics of river mouths, which is tied to climate change and regulation, and the dynamics of tidal deltas. Deltas and the shoreline at the river mouths are very sensitive to changes in riverine discharge, rainfall in the drainage basin, and also affected by regulation by construction of major dams. So sediment arrives at the river mouth in pulses during major flood events, and in between these major flood events, the waves rework the sediments and gives origin to this beach ridge plains. So any change in climates affecting rainfall in the drainage basin will affect the position of the shoreline at the river mouth. And we have here a nice example. The São Francisco River is the fourth largest river in Brazil. Since 1985, it has been completely regulated. But since 1985 also, the mean annual discharge has been dropping because of a change in rainfall in the drainage basin. You can see this in the lower right corner, this graph. In red, we have the stream flow, and in blue, we have the monthly rainfall. And you can see that during this interval, especially from 1985 to the present, rainfall in the basin has decreased, and also a stream flow at the river mouth. And this end up producing extensive erosion of this river. And this is simplified by the destruction of the Cabeço village, originally located at the river mouth. We also have to take into account that erosion does not destroy sediment, it just moves sediment from one place to other. So the sediment that has been eroded from the São Francisco River mouth, it has been used to make the shoreline prograde immediately downdrift. of the river mouth. So in wave-dominated environments, if the shoreline erosion is not caused by a rise in sea level, the erosion has to be compensated by progradation somewhere else. The other major cause of shoreline erosion in Brazil is this dynamic of tidal inlets. The epitidal channels moving constantly from side to side, and this causes a rearrangement of sediment in both sides of the tidal inlets, as you can see this in this animation. So the total volume of sediment remains about the same, but we can have extreme erosion, and we have extreme erosion alternating with progradation in the opposite sides of the tidal channel. Another kind of example is when the tidal channel is blocked by a sand spit, and eventually this sand spit is breached, like in this example, sometimes in one place, sometimes in two more places, and you can have severe erosion. So to conclude my intervention here, my contribution to discussion, this paper that has been published 2 years ago, they made a survey of shoreline erosion in the entire world, and they using satellite images from 1984 to 2016, and they concluded that 24% of the world's sandy beaches are eroding, 28 are accreting, and 48 are stable. And what I just said is that if we have erosion of the shoreline in a wave-dominated environment, and if this erosion is not caused by a rise in sea level, this sand has to be moved to someplace else and cause progradation. So those early estimates that, like for example, in Bird's book, that says that 6 to 70% of the world shoreline is eroding is not true. Okay, and at this point, I end up my intervention, and thank you very much for your attention.
Thank you, Landim. This is excellent. You gave back a minute to us, which we would take very gladly. But really, really interesting presentation as well. Thank you. Let's segue into our third presenter, Sérgio from the University of Azores from Portugal. You have the floor, sir.
Thank you. Okay, so let's see if it's now working.
We can see your screen. It is.
It is? Okay.
Perfect.
So I will talk about extreme coastal erosion, because I will talk now about the destruction of an entire island, and how this island is important in terms of paleontology, and it is so important that it was made a paleo park. So let's move now to the Azores in the central North Atlantic. And in the Azores, this is an Atlantic archipelago made of 9 islands. All of them are volcanic oceanic islands. And Santa Maria, in the eastern corner here, is the oldest island with about 6 million years. And this island is also the only one that is plenty with fossiliferous outcrops. Since about 20 years ago, we have been studying this island. I have organized a series of international workshops that we called Paleontology in Atlantic Islands. And as a result of this scientific effort, a multidisciplinary team was assembled. And we have geologists, paleontologists, and biologists working together in the field. And we know very well the outcrops and the shores of this island. Here you have some of the outcrops that have an age ranging from the late Pliocene to the Pleistocene. And all of this island is made of the coastal is quite high. This is an island that has been uplifted from the bottoms where the volcanic edifice was built. And around this island, we have several outcrops. Here you have just 2 of them, Pedra Pica and Ponta do Castelo. And as it is difficult for us to reach these outcrops, we go by boat, and we rely on the expertise of very good skippers that just put us where we want to disembark. And so this is just some views of the field work that we have been doing, and all of the strategy that is related with this scientific endeavor, which also includes, of course, coastal erosion, relies on a holistic approach. And we have 4 main processes that we explore in detail. So we have the geological processes, where we study the geology of the island and establish the main ontogenetic states of the island. We studied in the very, very high detail the island shelf and the shelf sedimentary bodies, because highland slope is really important for us. Biogeographical processes, glacial interglacial cycles, which have a huge impact in terms of the marine biota, and of course paleontology, with the production of very detailed checklists and quantitative data that allowed us to reach conclusions regarding geographical range, expansion and contractions of shallow water marine animals. And just a few slides showing part of this work. This work was done by a team of geologists that is based in the University of Lisbon. The leaders of this team are Ricardo Ramalho, José Madeira, and also Rui Quartal. So all of them are Portuguese scientists, and we were able, as a result of a paper that was led by Ricardo Ramalho, to establish with a very high accuracy the geological ages, the geological, as well as the geologic evolution of Santa Maria Island. And quite interesting, this island first suffered from a subsidence trend that reached about 100 meters per million year. And in a certain place, in a certain time period of about 1 million year, this island was completely destroyed because there were no volcanic eruptions in the island, and the first island of Santa Maria was completely destroyed. So it became a razor island, a guayot, with the top that was raised by marine erosion. So this is the best example I know of extreme coastal erosion in terms of a volcanic oceanic island. There is other islands where this also occurred, and later on, the island inverted from a subsidence trend to an uplift trend, and due to new rejuvenating volcanic history, there was a new production of volcanic products, and the second island of Santa Maria was created with first submarine lava flows and then subaerial flows, and this is more or less the history of Santa Maria Island. In this slide, you can see the first subsidence trend and then the uplift trend of about 60 meters per million year. This is the work that was led by Rui Quartal and shows the dynamics of coastal erosion, accretion of sediments, and accretion of new lava flows. So the island area may increase or decrease depending on which stage of the island we are here talking about. This is another paper that was published by a PhD student of Rui Quartal, Alessandro Ricci, and he published, based on boomer profiles, we were able to establish not only the location and the number of the main subaerial terraces related to former coastal erosion. Those are the ones that you see here on the eastern section of Santa Maria, but also the submarine terraces that you can see right here. And these submarine terraces, these submarine terraces are only 5 in contrast to the 9 subaerial terraces that that are visible on the island itself. So all this new data, this is quite recent, it was published in 2018, this new data allowed us to have a better image of the uplift rate, and it changed from a rate of 59 meters per million year between 3.6 and 2.15 million years ago to 42 meters per million year between 2.15 and recent times. And so This is really important. Here you have a complete view, an overview of the detailed bathymetry as well as the altimetry of the island. And this explained, or was able to explain for us, a kind of an enigma. All of this are the subaerial terraces and also the submarine terraces here on the left corner. And you see that most of these terraces are polygenetic. By this, I mean that they were produced by either low stands or high stands associated to glacial episodes and interglacial episodes, respectively. And in Santa Maria, we only have fossils with about 5 million years ago, and only the other fossils are those that are related with the last interglacial, those fossils right here where I'm pointing. And so we have only fossils from what we call the marine isotopic stage 5e, that is the last interglacial, and there is no fossils from any of the others. And now we know why, because all these previous places and sites on the coast, on this marine terrace, where probably fossils were able to be preserved in the fossil record, were eroded by subsequent interglacial episodes where sea level was high enough to erode all the older fossils. So we only have the remnants of the last interglacial. That's the explanation for the non-existence of marine fossils since at least 4 million years ago. In terms of paleontology, and now I will move rather quickly, we have made the geological history of each outcrop. We know the geological aspect and the geological history of all these fossiliferous outcrops. We have published a lot of papers regarding the fauna that is associated with these outcrops. We have studied the paleoecology, relying on many taphonomic issues, for instance, which allowed us to make paleoecological interpretations for each of this outcrop. And all this information is based on very high quantitative data that is related with the very important and time-consuming sorting of all the material that is collected. And we, as a conclusion of all this scientific work, we are able to get the paleobiodiversity of Santa Maria Island, which is quite unique in terms, sorry?
2 minutes, sir.
Okay, I'll finish in time. This island is really quite unique in terms of its paleobiodiversity because it has, for instance, whale bones, and in the over 20,000 islands that we have nowadays in our planet, whale bones are only reported for 5 oceanic islands, and Santa Maria is one of those. We have a Pliocene marine fauna turnover. It means that all of the older fauna that is present in the fossil record of Santa Maria does not occur nowadays in the Azorian waters. All of these are examples that I'm just showing. This is related with deep time changes, with an equatorial shift of the borders between the biogeographical provinces. Here in red, you have the tropical provinces, and in orange, the subtropical province. And you can see that since the late Miocene, about 6 million years ago to the present, there is a global cooling trend in our planet. And that's the reason for today, Cabo Verde to be outside in terms of marine biogeographical relationships regarding the northern archipelagos of the Azores, Madeira, and Canary Islands as well. And so we studied all these outcrops, these fossiliferous outcrops, and we discovered that 2 of them have an international relevance, which are Ponta do Castelo and Pedra que Pica. Pedra que Pica is this one. It has a very large area. Some of this outcrop is now underwater, and this is the whale bones that I'm talking about, and that they are really extremely rare in terms of all volcanic oceanic islands that we know. And due to the scientific relevance of the paleontological context of Santa Maria, the regional government of the Azores was able to protect all of this island as a paleopark. And this is the first worldwide paleopark that protects an entire island in our planet, as a matter of fact. So this process began in 2010. It ended in 2018 with the acceptance of Paleopark Santa Maria by the local government of the Azores. And we have this scientific endeavor as results with economic impact. That is something that the media and the public in general always demands to researchers. They always want something that is applicable and as an economic revenue. So here you have the fossils route, and besides this fossil route, I'm just showing a few images. The media talks about all this all these scientific expeditions and the results. We have published a lot of books. There is many TV programs that were produced and broadcasted in the national Portuguese channels. And this is a book related with the Paleo Park itself. And there is a scientific museum, a research center that is called the House of Fossils, and which is based in Santa Maria Island as well. So that's
excellent,
it.
excellent,
Thank
excellent
you very
work.
much.
Excellent work. Thank you very much, sir. Really appreciate this presentation. Some really amazing piece of work going on there. Let's invite Dr. Christine Omuombo from the University of Kenya to please make her presentation. I am also addressing these panelists through a private chat and sending questions to you ahead of the session. So please monitor your communication. I'm speaking to the panelists now. Christine, over to you, ma'am.
Hello, everybody. Thank you for this opportunity. Are you able to see my screen?
Yes, ma'am.
Okay, thank you very much. So I'm going to give you a perspective from the Western Indian Ocean with a special reference on coastal erosion in Kenya, which is something that is recent in terms of scientific studies, as there are gaps in what we currently understand. So when it comes to my presentation, I will just give you an introduction of the Kenyan coastline, some of the causes and impacts of coastal erosion, as well as what are we doing in terms of the coastal zone management, emerging issues, and current ongoing projects. Kenya is in Eastern Africa, so we are not in the Atlantic coast, but we are on the western side of the Indian Ocean. And here, that's a map of Kenya that shows you we have about 600 kilometers of coastline, which is relatively narrow compared to others and is dominated by fine sands, silts, and mud. And the main activity in these grounds when it comes to the livelihoods of the communities is fishing by artisanal fishermen and sometimes commercial fisheries. And when it comes to a coastal ecosystem, we divide it into the northern and the southern coasts, where we have a lot of infrastructure for tourism. And tourism is the key GDP earner within this coastal zone. So this is a map from 2007, which needs to be a bit updated because we have more hotels that are coming into play in this particular area. And with about coastal tourism bringing about 4.1% of the national gross domestic product, there has been more concerns in terms of how does coastal erosion impact on tourism in the current status. But then also along this coastline, we have other economic activities where we have maritime transport, with the port in Mombasa being the largest port in Eastern Africa and serves other landlocked countries such as Uganda, Rwanda, the DRC, and Southern Africa. And we have a new project that is known as the Lamu Port that currently has 3 berths completed, and I will discuss that a little bit later. But we also have inland agriculture that is taking place within this particular area. And we have the fisheries, we have some mining ongoing, we have manufacturing as well as salt mining that is a bit different. Our coastal zone has 3 typologies where we have the old delta plains further north that is dominated by the Lamu Island, where we have the Lamu Archipelago. Then we have the modern day Sabaki Tana Delta Plains, and this is where we have 2 key rivers that supply sediments to the coastal system, and that is the River Tana and the River Sabaki. And then we have the raised reefs and limestone plains in the southern coast. So it's relatively simple, but there are dynamics that are particular to the various areas. So when we go back into a little bit of what is happening in the older type plains, we find that this comprises of a small archipelago of islands in this particular area, where there was it was cut off during the late Holocene, and you're finding that there is a deficit of sediments in this particular area, and there has been some slow progressive loss in terms of the island beaches, the beaches within this particular island, and the replenishment comes in from the dunes that are located in the islands. So these dunes are eroded, and they supply there's the longshore sediment drift, and it supplies the beach sediments within the particular islands. This is not sustainable, considering it has a negative deficit budget, and therefore we are looking at, in our current project, looking at how can we address some of these issues, and also understanding the dynamics of that particular sediments in that area. When it comes to the Sabaki and Tana Delta plains, here we have a large supply of sediments that is coming from inland, and just to note that these rivers traverse from almost the center of the country in Mount Kenya, where they originate, all the way south towards the coast. So we have a large amount of sediment supply that is coming to this shoreline, and we have it exhibits a lot of beach erosion and accretion areas that can be seen in some detailed study that I will highlight. And in that particular area, we find that in this diagram, we're showing you just a bit of the shoreline, where we are finding the dune ridges and where we have some coral reefs in the central area. And detailed studies have been carried out in this Malindi Ugwana Bay area, where we are finding that the shoreline has shown some progression of up to 750 meters over the last 40 years. But we're trying to update this with our current research, as there's been a lot more focus on conservation within the coast. And we are finding that in certain areas, there is an accretion rate of up to 5 meters per year, which is relatively high for this particular area. And then we're also finding that you have in other areas about 6.3 meters accretion per year. And so trying to address some of this is what we are looking for in terms of enforcing policies in these areas. And then further south, where we have the raised reefs and the limestone plains, we're finding that the erosion within the terraces, and most of this area, it's predominantly very touristic. You have these new resorts that are coming in, new seafront apartments, and everybody is building up these new seawalls. And these seawalls are supposed to contain the erosion problem, where they're trying to say, okay, we can still have our properties and beautiful beaches, but that's not working, because you're having drawdown of beaches in most of the areas from about 2 to 5 meters currently. So that then is now becoming a new issue, and we're hoping that we can address that. And some of these issues that are occurring is basically the development along the coastline currently does not have any integrated coastal zone management plans that have been implemented. And that means that we are having very sectoral components coming into play. So you find that within the tourism, within the agriculture, with everybody doing their mining, they have their own regulations, but it's one coastline, and everybody else is concentrating on conservation, and we're not looking at what the sediments are doing. The current National Environmental Management Agency is trying to institutionalize the ICZM principles, but then we have this action plan that needs to be harmonized for the particular area. And it's been back and forth over the last 20 years, but we're hoping that there will be some success maybe in the next 10, I'm not quite sure, but we do not lose hope with our policymakers. But then as is, we are signatories to various multilateral environmental agreements on the coast and marine environment. And that means that we are trying to, we are able to, as researchers, to apply for certain funding for very interesting projects and implement that. And I think the other aspect that comes in is because we've not been engaging with our communities when you're doing our studies and the management of the coastline. Now is when we have the construction of beach management units that are coming into play to help us in terms of the research, in terms of resource monitoring, and in terms of the management of the coastal zones. And then we also have current resource management tools where we have this environmental impact assessments, we have environmental audits, we also have the marine protected areas that are coming into play. And this, the successes of some of this are becoming quite important when we're looking at the management of our coastal zone. But then we have this emerging pressures. We are a developing economy, and we have a vision to achieve in 2030. And also we would like to have these SDGs that are being integrated into our systems. And with the blue economy coming at the forefront, it presents an opportunity for sustainable development. But at the same time, we are having rapid expansion within the population, increased exploitation, and also we're trying to develop that in strategies to be able to manage our coastal systems. One of the major development projects that we currently have is the Lamu Port, where within this Vision 2030, we're trying to have one of the largest deep sea port in Eastern Central Africa that will have a cargo capacity of about 40 million tons per year. And to achieve this project, we obtained 1,000 acres from the Indian Ocean. And this, we know that it has significantly affected the marine ecosystems. And this is located in Lamu, where we have a lot of mangroves that had to be cleared to make way for this port. But here we're finding that the natural infrastructure is suffering at the expense of this new built infrastructure that we're getting. So here we have ongoing dredging of about 32 deep sea berths that will be 18 meters long, 18 meters deep, 400 meters long. And we hope that we'll have about 6 kilometers of that particular coastline. And there was no initial assessment of what the sediment dynamics are, and we are interested in that, and also just to see without the mangroves, how will that play in. We also have major developments in terms of oil and gas exploration, and we're looking at having in new resort cities and having a new coal and wind power stations that will be located especially in that Lamu coast, which is now becoming very fragile ecosystem.
Less than a minute, ma'am.
Okay, so those are some of the emerging issues. We also have further upstream agricultural projects, and then mining, maritime safety, and climate change that is becoming a threat. Currently, we are collaborating with a lot of local and international partners to understand a little bit more of the sediment dynamics in the Lamu archipelago. And in here, we are trying to work within the mangroves ecosystem and also just understand how the sediments are affecting the mangroves and emerging pollutants such as plastics that are also being found in this particular areas. I think that's the end. Thank you very much. Obrigado.
Thank you, Christine. I appreciate that very much. Some interesting work going on there on the eastern coast of Africa. Let's invite Joni Backstrom from University of North Carolina, Wilmington, to give his presentation, please.
Thank you. Can you hear me?
We can.
Okay, and you can see my slides?
Not yet.
Okay. Try again.
Good. Project it now. It's not in projection mode yet. Perfect, sir. Go ahead.
Good. Great. Thank you so much. Again, thank you, everyone. Thank you, panelists. Thank you, Jimmy, for moderating this. My name is Johnny Thomas Backstrom, and I'm with the University of North Carolina, Wilmington. Obviously, we only have 10 minutes to give a quick presentation. We've had 4 hurricanes here in North Carolina over the last 4 years, which is quite significant. And we've been monitoring a lot of these beaches, the South Coast and the East Coast. We probably have about 18 stations that we've been monitoring very frequently, especially right before and after storms, to really examine and understand some of the coastal processes taking place there. Just a brief overview. This is from NOAA. Again, you can see that North Carolina, you can see the white box right here. Again, North Carolina is very much kind of in the eye of the storm. Here's a few direct hurricanes over the last 150 years. So again, lots of activity there. The focus of this study will be on 4 hurricanes that have again occurred recently. We had Matthew, which was a Category 1 in 2016 that made landfall just near the North Carolina, South Carolina coast along here. Then we had Florence, Category 2. You can see the track of Florence. It made direct landfall in Wrightsville Beach. Category 1, Category 2, they're still deciding on that one. That made Wrightsville Beach direct landfall, and I'll be discussing that briefly. Then 1 year later, That Florence was 2018. 2019, we had Dorian, again, a massive devastation in the Bahamas. I'm sure you all remember that one. That just skirted off the coast of North Carolina. It was quite scary for many days. We didn't know exactly what track it was going to take. And then just recently we had Isaias 2020, which just made landfall on the south coast of North Carolina just about 6 to 8 weeks ago. So again, lots of activity there. Lots of damage from these. This is from NOAA, 24 billion in damage from Florence. Again, that was in 2018, 9th most destructive. And we had 30 deaths associated with that one. A very slow moving storm, lots of flooding and damages from that. Some recent news: hurricanes near US coast forecast to worsen and multiply due to global warming. That's a Washington Post, and this was just in September. Notice the image here that you see, that is Southport, which is one of those south-facing communities right here in North Carolina. So massive destruction there to some of the marinas. We also, another one, climate change is making hurricanes stronger. Researchers find this, that's from the New York Times. And again, the hurricane they're showing there is Florence. So again, just recently, 2 of them very much focused on North Carolina. So just briefly, the Southeast, actually most of North Carolina consists of a series of barrier islands, but Southeast North Carolina, we have these long, narrow, low-lying barrier islands that extend along the east coast of North Carolina and the south coast. These are separated by tidal inlets. Many of these islands are nourished periodically. In other words, we take sand from offshore and pump them due to high tourism. We also have some protected reserves, Masonboro Island right here, which I'll be discussing in conjunction with the study. We have average wave heights about 1 meter, and then during hurricanes, we might have 5-meter wave heights offshore. Average tidal range, microtidal, right around 1 meter. And our erosion rates range from stable for our beaches that are nourished to areas like our nature reserves, where some areas we're seeing erosion rates as high as 10 meters per year. And on the bottom along the left, you can see some of these kind of typical tidal inlets and some of the beaches we have in the region. The main method we use is we use an RTK GPS. So again, very high resolution, centimeter scale accuracy. You know, we're talking a couple of centimeters vertical and horizontal accuracy. The beautiful thing about this, it's fast and efficient. It's light. We don't need to set up any kind of base station to do the work. We have a tablet. We log into a local reference station, and we are good to go. We also have a wheel on there. So the idea is we can run these profiles from the dune line or even beyond the dune line straight to the beach. And we typically run maybe 3 or 4 lines along the beach. After the storms, or if we want to do a post survey, we can come back and come back to exactly those locations. And again, we can export the tablet data straight in shape files into a GIS program. So again, that's some of the main methods. Here's some output results. Again, we can see, if we're looking at the top left, you can see kind of red lines indicate a pre-storm, and then the green line represents post-storm. So again, close line spacing and accuracy with these things. We can generate digital elevation models from this. We can subtract them using GIS. But for purposes of this presentation, we'll be looking at some of the profile changes as shown on the bottom left. We also use a GPS-enabled camera, waterproof, which gives us direction, location, height above sea level, and again, just a nice way of kind of illustrating some of the changes that we're seeing along the coast. Sometimes it's very difficult for me. I'm an active surfer, and sometimes I'll go out and decide to run a survey, but then often right after a big storm, we get these beautiful waves coming in, and I often debate whether I should just go surfing or surveying, but you know what, science always wins, and I end up running my surveys first. But then I have brought my board with me lately. So main observations, I'll just try and go through this quite quickly. This was just outside of a window from Hurricane Florence. So we're about 10 miles inland. We saw these big longleaf pine trees just come crashing down within 10 minutes. My kids and I saw about 4 trees come down, snapped like toothpicks. So that was Hurricane Florence. 90 to close to 100-mile-per-hour winds. So again, that was just outside my window. For purposes of this talk, I'll be looking at 2 islands. We're looking at Wrightsville Beach to the north. This is a developed, renourished, and very stable beach, again, mostly due to the nourishment, separated by Masonboro Inlet. It's a jettied inlet system. And then we have Masonboro Island, which is about 13 kilometers long. Again, a natural reserve, part of a National Estuarine Research Reserve System, undeveloped with very high erosion rates. You can see some of the survey locations. We kind of have a northern, central, and southern Weitzel Beach, and then we focus kind of on the central and southern parts. With Masonboro Island, again, a very narrow protected natural reserve. If you look at the top right, you can see the narrow nature of it. In many cases, it's only about 100 meters, wide in most instances. Here's some examples from Matthew. Again, if we look at this image here, we have the beach to our right and the marsh to the left. Again, notice a very narrow, low-lying features here, and we often get these temporary inlets and breaches during these big storm surge events. On the bottom left, you can see some of these fresh washover terraces as that sand comes from the beach and gets deposited on the backside. So we get this classic barrier rollover process. And just to illustrate it, again, if we look at the profile here, the pre-Matthew is shown in this dashed line here. The post is shown in the dark line. Again, you can see the top of the dune gets eroded and a lot of that material gets deposited in that back barrier marsh area. So we get this rollover process. So we're just trying to illustrate some of the ongoing mechanisms that are very typical for this low-lying barrier island. If we move north towards Whitesville Beach, this is very northern Whitesville Beach. This is again an inlet hazard area. So we have an inlet very close by, a small, highly migratory inlet, Mason Inlet. Again, some of the just key points I'm trying to show here is if we look at this profile right here, this was right after Hurricane Florence. And again, notice how straight the profile has begun. So we're starting to see kind of one of those storm signatures is this profile straightening. And then within 1 year, so this is just an example of 1 year, we can see this massive berm buildup as the beach begins the recovery process. So, you know, here we're talking 30 to 40 meters in some cases within a year. So very large changes taking place quite quickly. Massive recovery. Again, this is just 1 year after. If we come to our central location, this is Central Wrightsville Beach. Some of the key messages I want to show here is if we look at the top, we have the pre-photo and then post. You can see all the sediment deposition. A lot of these dunes have been completely smothered by sand as that material has been moved up from the beach. So again, slow recovery here. But again, if we look at our pre is shown in blue, that's the profile shown right along here. And then our post is the orange, sorry, let me go back. We have the orange line shown here. So again, direct impacts of the storm within a few days of the storm, we have this massive erosion taking place. But we also have this dune base accretion. So we believe a lot of this material is actually being pushed up onto the dunes, but we're not seeing the rollover that, or the transition to the back behind the dunes as we have seen with Masonboro Island.
You got 2 minutes, Joni.
Okay. Real quick, minor change in Southern Wrightsville Beach. Again, quite a stable area. Again, notice this profile straightening. This orange represents right after the storm. So again, I like to call this coastal Botox or wrinkle removal. Again, what the hurricanes tend to do is they tend to take any irregularities and kind of form this straight, kind of a concave shape profile that we're seeing. So again, this part of the island was relatively stable towards the south. General views, we have this profile straightening in back beach accretion. It's a common storm signature, and then we have this berm buildup. Masonboro Island is ongoing rapid retreats, rollover, and potential breakup, especially if we have a larger system in the future. Wrightsville Beach, again, we're seeing different responses and recoveries within the same barrier island itself. So there's some questions to be asked why we're seeing such differences. So obviously we have this regular renourishment, but is there an influence of the inlets? And is there an offshore influence? So in some ways, we're seeing short-term hurricane impacts tend to reflect the long-term change that we're seeing in these different beach systems, even within the same beach. So we want to examine for future work, examine the influence of offshore geology and morphology, look at the inlet ebb channel orientation as Landim was talking about, and morphology, and some wave modeling. So further thoughts, beaches only represent the tip of the iceberg when it comes to the wider coastal zone. So the question is, what role does the surf zone and shore face play in coastal response and dynamics? And for that, we plan to run some wave models. This is not my image, I've taken it from elsewhere. But again, we're already running the bathymetry survey, side scan sonar. We have wave buoys offshore. So we're gonna start running some of these wave models to really understand if we're seeing differences in wave forcing along these different beach segments. And that's all I have. Thank you very much.
Excellent, excellent. Thank you very much, Joni. I'm not sure how to do this, but I feel like requesting for a virtual round of applause for for our excellent presenters today. We have had an amazing set of presentations. Thank you very much. Some questions have come through on the chat box that we have. So we are just going to move on right into the Q&A session. We've got 15 minutes for that. If you are listening and participating and you have questions, please use the chat box and get those questions to us. We will take some in this panel, in this session. We have to end in about 20 minutes, this public broadcast part of this. And then we will go into a breakout room for 30 more minutes. And in that room, we'll be able to address additional questions and have a conversation actually as well amongst the panelists. Okay, send us your questions. So the first question goes to our first presenter. So I'm going to ask Dr. Goncalo to address that question. And that I've sent that question to you. It's really a little bit about the impact of permafrost melting, the impact on coastline, perhaps causing ground sinks and maybe even lake formation. Over to you, sir.
Okay, can you hear me?
Yes, sir.
Yeah. Okay. Thanks for this question. It's really a very interesting question. I was focusing so much on the coastal processes, especially those relating to the ocean itself, that I forgot probably to emphasize on the changes associated to atmospheric warming. And in fact, most of this area of the Arctic is warming significantly, and permafrost, which occurs also inland, is warming. It is warming significantly, and as it warms, there is a thickening of the upper part of the permafrost, which normally thaws or melts every summer, and it's thickening from year to year. And in some areas, this thickening, especially when there is significant ice content on the permafrost, because there is variability on the amount of ice which is frozen in the ground. When it's excess ice, normally it may lead to collapse of the ground, and there are lakes forming, as it's mentioned in the question. And the area, in fact, looks almost like a cheese surface when you fly it from the air. And there are a large number of lakes. These are called permafrost thaw lakes, and the process is called thermokarst. And it generates subsidence, mainly in these in the flatter areas in the coastal plains. But when where the ground is sloping, when you have sloping surfaces, you also have thaw slumps. These are retrogressive thaw slumps associated to the warming, and they can occupy really very large areas. In fact, the interaction between the coastal erosion processes, mostly wave generated or even thermal erosion by the warm seawaters, reaches frequently these areas with lakes by the coast, and there are events of quick lake drainage, which are essentially catastrophic events of lake drainage, and these will also have an impact on the dynamics of the coast. So yes, so there is a widespread effect on atmospheric warming. And there is, besides the marine processes, there is also a significant increase in permafrost degradation and erosion processes, which will add up to the marine dynamics. Of course, all these terrestrial processes will have an influence on the drainage systems, which feed sediments into the marine system and into the nearshore zone. Yeah, I think I hope I answered the question.
Yes, you did. Thank you. Thank you very much. We've got a couple of questions actually for our second speaker, Landim. So let's see, you go ahead, Landim. Why don't you address the question on hydropower, hydroelectricity?
Yeah. dams, usually they affect the sediment supply to river mouths, okay? But this relation is not so straightforward because dams and the regulation of river flows, they cause changes in the backwater behavior of the lower river course. During normal flows, the surface of the water diverges from the bottom of the river. So usually have a deceleration of flow and accumulation of sediment. And during the floods, the inverse happens. So the surface of the river water is higher than the surface of the river, the waters in the receiving basin, and then you have an acceleration of the river flow. So we think that in the example that we mentioned, the San Francisco River, the regulation is what caused erosion of the shoreline at the river mouth, because with regulation, we eliminate the big flows. So we do not have anymore what we call a drawdown effect that would accelerate the flow and remove sand from the lower river course and deliver this sand to the river mouth. So in this case that I reported, I think that the major cause of shoreline erosion is not because there is no sediment. There's enough sediment in the low river course. The problem is that the regulation affected the backwater behavior of the river. So it's not able to deliver sediment at the river mouth as it did before. I agree that in a long period of time, what will happen is that eventually the dams will retain bad load sand and then usually make an impact at the river mouth. But we still do not have enough time to propagate the signal of stopping bad load at the river dam and propagate this signal up to the river mouth. Okay.
Thank you. We have, why don't you segue into the next question?
The next question about the socioeconomic.
Yes, your work shows really important conclusions there that you drew. The accretion and the erosion and accretion is actually sort of almost balanced out, you know.
Yeah.
And have you what? There might be some additional perspectives if you look at the socioeconomic impacts of erosion versus accretion. Can you speak to that, please, sir?
Yeah, I think that's one of the few cases in which shoreline erosion implies in loss of sediment to the offshore areas is when the shoreline erosion is caused by a rise in sea level. Like when we have a hurricane, you have a momentary rise in sea level, so you lose sediment from the shoreline and move it offshore. And if sea level is rising, you're going to move this sediment permanently. But concerning the socioeconomic impacts, most of the coastal zone in Brazil is occupied by people that gets reasonable good salaries. Is a region where the property is usually expensive. Okay, and there are some. So it's not a phenomenon that is affecting more vulnerable people, except in very specific situations. Okay, and we have some legislation in Brazil, for example, that requires a 30-meter setback from the high tide line, where no permanent construction is allowed. In some states, we have a setback of about 60 meters, but there is no provision in the present regulations of a setback that it tries to address the problem of shoreline erosion where it exists. Okay, so it's something that still needs to be incorporated in the coastal management. Although I have had the opportunity to participate in some projects where the environmental organizations required that we could calculate a setback for a setback of no occupation. And we did that using the past historical rates of shoreline behavior, either retreats or progradation, and projections of future shoreline retreats using the several scenarios of sea level rise for the IPCC and recurrent intervals of storm events, the declivity of the beach face, and we end up with some numbers that has been used in the license process. The point is that people do not understand that the setback is a portion of the land that will eventually be lost along the years. And as soon as you have a major storm and have some localized erosion, they want to build some protection of the shoreline in order to avoid further loss of land. But I think from the socioeconomic point of view, it does not affect vulnerable population in Brazil.
Okay, excellent. Thank you for that response, sir. I have one more question for you, but before I, incidentally, Landim, you're such a superstar on this panel. All the questions seem to be going to you, Landim. But let me remind everybody on the session, including our panelists actually, that we have 3 additional parallel sessions that there's a session on extreme weather. There's another one on sea level rise, which connects with a couple of the conversations that are going on here. And then a third one on floods or flooding. So I would encourage everyone to post these sessions, find the recordings of those other parallel sessions, because there are intersecting concerns and issues here that will help. I wish we were, we could be in 4 places at the same time, but we cannot. All right, so we're down to about 7 minutes for this public broadcast session. I want to remind everyone, please, that just stay put. You will be moved to a breakout room, actually, and this session will continue for another 30 minutes, and we'll be able to have some additional interactions. Okay, Professor Landim, as shown in your presentation, the erosion present in Northeast Brazil has major control over the low sediment supply over time. Is there any evidence that sea level is rising in the Northeast in the last century?
Well, sea level behavior in Brazil is a little bit different from the Northern Hemisphere during the Holocene, for example, because we are in what we call far field from the GM models, the compensation of changes in loads of ice and water in the planets. So during the last 5,000 years, the relative sea level of Brazil dropped between 3 and 4 meters. It's different, for example, in the United States, the East Coast, where sea level along the entire Holocene has been rising. In the Brazilian coast, almost the entire Brazilian coast, because we are in the far field region, sea level has dropped 3 to 4 meters. Okay, so Our coastal plains are not exactly flat. They were not constructed as a stable sea level, but a drop in sea level. So this will have an effect in the flooding in the case of a future sea level rise as predicted by the IPCC reports. Okay, so we have evidence from tidal gauges along the entire Brazilian coast that more recently sea level is rising, as is happening in the entire world. But at this point, the amount of rising sea level is so small that we cannot account the causes of erosion along the coast. We cannot associate the cause of the erosion that we have along the coast with such a small rising sea level. Certainly in the future, the problem will aggravate, but the present day erosion that we have along the coast, we can explain it perfectly using this long-term approach or using the short time processes like the dynamics of river mouth and tidal inlets or construction of ports and other inadequate uses. But so far now, I don't believe that the rise in sea level that took place of few millimeters in the last decades, they are enough to explain the causes of erosion that we have in coastal Brazil.
Excellent, excellent. Thank you, sir. May I, on behalf of the organizers of this summit, thank our panelists for just excellent presentations.